Welcome. In this video lecture, we will perform some numerical practice on network functions. Suppose we have this network where we have a capacitance connected in parallel to a resistance and an inductor like this, and we are required to find out the input impedance function. As you can see, it only has the input ports, it does not have the output ports, so it will be a single port network. So the input impedance function will be nothing but the driving point impedance function. That means we are required to calculate Z11 of S, where Z11 will be equal to V1 of S divided by I1 of S. As we can clearly see, we need to calculate the impedance seen from the port 1. So what we need to do, we need to represent all these elements into the S domain first and then calculate the impedance seen from the port 1 from this side. Then the impedance seen from the port 1 will be termed as Z11 of S, or the driving point impedance function. Here we have a capacitance. We already know in the frequency domain we represent it like 1 by Cs. We have this resistance. In frequency domain it is represented by R, and we have an inductor, it is represented as Ls. So to calculate the Z11 of S, we only need to calculate the impedance seen from this side. If we see from this side, we can come to know that R and Ls are in series and their combination is in parallel with 1 by Cs. So Z11 of S will be nothing but the parallel combination of 1 by Cs with the series combination of R and L. So it will be nothing but like this. So after calculating, I get 1 by Cs multiplied with R plus Ls whole divided by 1 by Cs plus R plus Ls. Taking the LCM and solving, I will get R plus Ls divided by Cs whole divided by 1 plus Cs in multiplied with R plus Ls whole divided by Cs. Further solving, I will get R plus Ls divided by Cs multiplied with Ls will give us LCS square. Cs multiplied with R will give RCS and plus 1. This can further be rewritten as Ls plus R divided by LCS square plus RCS plus 1. So this is the required driving point impedance function of the given network, where the given network was a single port network. Now suppose this would not have been a single port network. Instead it would be a two port network with the port 1 this side and port 2 this side. Then if we were required to find out the driving point impedance function, then we could do so. Let me erase it out. Now it is a two port network and we are required to find out the driving point impedance function. For a two port network, the driving point impedance functions are Z11 of S, the impedance seen from the port 1, and Z22 of S, the impedance offered by the circuit or seen from the port 2. For the given problem, as both the branches are connected in parallel, whether I see the impedance from this side or from this side, it will be the same. So Z11 of S will be same as that of Z22 of S, and it would again be equal to 1 by CS in parallel with the series combination of R and LS. And if I solve it, I will come up with LS plus R divided by LCS square plus RCS plus 1. You can see that this impedance is coming as in the function of as a function of S in the form of numerator to denominator. This is numerator, a polynomial function, polynomial in S, to the denominator with a polynomial in S. There are some things to be noted here, that the denominator polynomial has s square, s, and s raised to power 0. That is, all the terms of s are present. Similarly, in the numerator, numerator has s raised to power 1 plus s raised to power 0. That is, numerator also has the terms of all the terms of s, that is s to power 1 and s raised to power 0. No other terms are missing. Also, the numerator and denominator, the maximum power of numerator and denominator are differing by either 1 or 0. Over here, the maximum powers are differing by 1 and the minimum powers are differing by 0. That is, they are same. The minimum power of s over here is 0. The minimum power of s is also 0 here. So we can write the general expression for any impedance function. The general form for any impedance function will be, so the general form of any impedance function or the admittance function will look something like this. It will be the ratio of two polynomials in S, where this is the numerator polynomial and this is the denominator polynomial, where the degree of this polynomial is n and the highest degree of this polynomial is m, and there is a condition that the difference between n minus m should not exceed more than 1. It can be 0, it can be 1, but it cannot be more than 1 for any physical condition or for any physical system. We'll see it further. We'll derive a certain relation for this. We'll prove it later. Let us see some more examples. Here we have a resistance and an inductor connected in a two-port network like this, where this is the port 1 dash, and this is port 2 and 2 dash, like this, where the resistance is R and the inductor is L. We need to find the Z11 and Z22 of S. Along with it, we need to find Z21 of S and Z12 of S. As already stated, Z11 of S will be equal to the ratio of V1 of S divided by I1 of S. So that means it can be calculated by calculating the impedance offered by this network seen from the port 1 only, when all the elements are represented in S domain. So first we need to represent these elements into S domain. Here we have a resistance. In time domain it is represented by R, and in S domain it is also represented by R. But in case of inductor, in time domain it is represented by L, and in frequency domain or S domain it is represented as LS. So now the circuit is represented, or the network is now represented in the S domain. We can calculate Z11 by seeing the impedance, or by calculating the impedance seen from the port 1. So we can clearly see, if I pass a current from this terminal, it will flow through R and then through L, and then it will come back to this 1 dash terminal to complete up the circuit. So that means if the current flows like this, so the impedance offered or seen by the current into the active network would be R in series with the inductor, so the impedance would be written as R plus LS. This is nothing but Z11 of S. Similarly, if I had to find out Z22 of S for the same network, then this current would not be here. This current will not flow. I should mark the current from this side only now. So when the current passes through this terminal port 2, the current will pass through this and will eventually flow into inductor only. There will be no current flowing into the resistance. We have to keep it open. So while calculating Z22, we will pass a current through the terminal 2 and we will see what impedance it sees into the circuit. So Z22 will be nothing but LS only. So Z22 is LS. Now to calculate Z12 or Z21, Z21 will be Z21 of S. This will be V2 of S divided by I1 of S. That means I need to find out a relation between V2 and I1. It means this is the excitation and it is the response. If it is the response, we will consider this terminal to be open. That means this current will not be flowing now. This current will not be flowing. The only current that will be flowing will be I1 and it will flow from this terminal and it will be like I1 of S. Now as we can see, this I1 is passing through R and LS and it is causing a voltage drop across this. Now this voltage drop will also appear across these two terminals. So V2 of S will be equal to the voltage drop across LS, and the voltage drop across LS will be the current flowing through it. It is I1 of S times the impedance of the inductor, which is LS. So V2 of S is nothing but I1 of S into LS. From this expression I can find out V2S by I1S, and this will come out nothing but V2 of S divided by I1 of S, and this will come out to be LS. So Z21 of S will be LS. Similarly, we can calculate Z12 of S. If we have to calculate Z12 of S, it means we have to calculate V1 of S divided by I2 of S. It means this is the excitation and this should be the response. If it is the excitation, it means the I2 will be flowing. So I have to erase out this current now. This time I1 will not be flowing. We will mark a current I2 of S from this. So the excitation is provided and we need to calculate V1 across these terminals. When I2 is flowing, there will be no current flowing through this resistance R. So that means V1 will be equal to the voltage drop across LS. So I can directly write V1 of S to be equal to the voltage drop across the inductor when I2 is flowing through it. So it will be I2 of S times LS. This implies V1 of S divided by I2 of S will be equal to LS, and this is nothing but Z12 of S. This is how we calculated the driving point impedance function and the transfer function for the given network. I will post some more video lectures related to the numerical practice on network functions. Thank you.